Good afternoon, everyone. Have a seat. Don't keep standing in the back. I hope everyone enjoyed their lunch or is about to enjoy their lunch. Hi, this talk is going to be about HTTP 2, the next version of HTTP. My name is Matthias. If there are any questions during the talk, if something not clear, or if I start to talk too much because I'm nervous, just stop me, raise a hand, ask a question. First, I'll cover what we are going to cover in this talk. That still gives you time to quit or leave the room if it's not to your liking. I'm going to give a bit of history on what HTTP 1.1, the current spec, or the newest spec is, how it works, so we'll dive into the internals a bit, what HTTP 2 tries to bring to the table, what are the benefits, what are the downsides, we'll do some performance comparisons, nothing live because I didn't trust the Wi-Fi, and we'll draw some conclusions, or attempt to draw some conclusions. First of all, my name is Matthias. I am in the PHP room, but I'm no longer a PHP developer. I'm one of the sysadmin ops guys. I write PHP for scripting, but that's where it ends. So I used to be a dev, but I'm now in ops, as they say. And I believe in DevOps. I believe in working together with devs, with you, to achieve the goal of faster applications, higher availability. No longer silos that have to fight each other or point fingers. I blog at this URL. If you want a recap of this particular talk, go to that URL /HTTP2. There's a lot of words on that page, but that tries to summarize this talk. Just a couple of plugs and then I'll promise I'll get into the content. I run a weekly newsletter about Linux and open source. It's called Cron Weekly. Tune in. If you don't like it, unsubscribe. That's how it works. And a small plug, Syscast, if you happen to be a Laravel developer and you know Laracast, this tries to do the same thing but for sysadmins or open source projects. It's in beta, nothing live yet. That doesn't matter. What is this talk about? First, what is HTTP? Because we can talk about it all we want. If we don't understand the internals, the basics, we won't get very far. It's a client-server protocol. Which protocol is it? It relies on something called a request and response. We saw this in the previous talk as well. You send a request, you hopefully get a response that you can parse. The current version, when I say current, I mean HTTP 1.1. So the, well, actually old version because it's been superseded by HTTP 2. It's been a standard since 1997. That's almost 20 years old. That's still the standard that we use today to build websites, web servers, web applications. And while it has undergone some changes in those 20 years, nothing major. So the websites that they built 20 years ago versus today still rely on the same ancient yet reliable piece of technology, which is pretty amazing. It uses the concept of metadata to describe a request. You want to make a request, you set some headers to describe what you can accept in response, what you actually want to retrieve, and you send that to the server. Without HTTP, without the protocol of HTTP, we would not have the web that we know today. We would still have networks, TCP/IP, networking, routing, but the web, as is relies entirely on HTTP, the protocol. In theory, it's a simple protocol. It's entirely plain text. It's easy to read if you see it in front of you, but as anyone who has tried to parse an HTTP output, you know that it can be tricky to parse. New lines, particular characters, not that easy. So, requests. We send a request to a server, to something that understands the HTTP protocol, and we expect to get a response. We'll do this URL as an example. What would happen if you were to browse to that particular URL? Well, for starters, your user agent, which is a term used to describe the browser, Firefox or Chrome, as well as if you do curl requests from within your PHP code, then you are the user agent. Whatever is connecting to it starts a TCP connection to the endpoint. Once you have that TCP connection, you send a set of headers to describe what kind of content you want in return. And it looks like this. The first header, which is plain text, so what you see is actually what you get in this case. You have to type or script this. You send a GET request, so the post, put, heads, etc., to a particular URL. Every URL starts with /. If you have a web page and it's a home page, well, that's just slash, even though the browser may not display it. You say what URL you want, and you say what protocol you are speaking and understanding. Which could also be 0.9, 1.0, anything that the server can know what kind of response that it should generate. You could tell the server what kind of response you accept, which is useful in API scenarios. Maybe you want a JSON response, maybe you prefer XML. That could be in the accept header. You'll also tell the server that the request you're sending, it allows to be gzipped or compressed. You accept an encoding once it comes back. It doesn't have to be plain text, it can actually be compressed. You also tell it what host you are reaching, because at the HTTP level, what you're actually doing is you're connecting to an IP address on a port, but if you don't tell them which virtual host, which website on that server you want, you'll just get back the default virtual host, which in many cases is just an empty host. So you have to describe what the URL, what host name, the host header you want to get back. And you could optionally describe who you are. Browsers do this if you ever tailed or looked at your action logs, access logs. You'll see Firefox, Chrome. Every browser tries to describe who he or she is. It's a simple key value system. You have your key, you assign a value, that gets sent to a server. The moment that there are new lines separated, the moment you have two new lines behind each other, that's when you indicate your request is done. You've sent all your headers, and at that point you are requesting or accepting a response from the server. Here's what this looks like. First, if you want to do this manually, you open a telnet session to a remote server. This simplifies what TCP/IP would do. You start a TCP session to a remote system, you send the lot of your headers that you want to send, and hopefully the server gives you a response back. Those are the three big parts of an HTTP request. The other side, of course, the response headers. Same URL that you are requesting. Once you've sent all your headers, once you've entered those double new lines to indicate your request is done, the server will start to parse PHP, Ruby, Perl, and hopefully send you back a set of headers to describe the response and the actual response. It'll start by confirming the protocol that you requested, the version that you wanted, status code, and an optional message. The message, by the way, can be anything. If you like to mess with your web server, this could say not found, but as long as it's a 200, your user agent will parse it correctly. The web server could or would respond with cache control headers, useful to indicate if this response is valid for the next couple of hours, so you don't have to re-request it. But it will also tell you whether or not the data it's going to send you is or is not compressed. So in former requests, we said that we would accept a gzip response if it's possible. Content encoding headers say that what is coming back behind or after the headers is about to be compressed. It will also tell you how long that data is, so you know if you're parsing it or if you're writing a web server. After those 9,944 bytes, you can stop the connection or stop parsing the content. And it can also tell you what kind of content it is. This could be XML, JSON, whatever the browser, the user agent could use to parse or to correctly interpret the value. And optionally, most web servers say what server they are. I don't really know the purpose, perhaps it's bragging rights. Default Apaches, for instance, would also tell you the exact version that they are running on, which is not that secure because you know what kind of versions to target. And it will tell you a date, which is used in comparison to a max age, to know the server generated is at this time, which is also when I first made this presentation. It's valid for that amount of time, calculated on whatever time the server generated it. So we have the same kind of key value pairs. Super simple, key, value. But it gets complex once the value wants to contain new lines or quotes or dashes or anything that could be interpreted as a command instead of just a value. So if you do this on any kind of website, you'll just see a lot of more headers. These are just the basics ones you'll see. Some send as much as 20 for caching purposes, for debug headers. It's a free game. Anyone can write any kind of value and it just gets sent. So you can also do what you often see are X dash number of variables. You can put anything you want in there. Okay. HTTP 2. So we know what HTTP 1 is doing. request response, plain text. What are we trying to solve with HTTP 2, the next version? First of all, and that's the biggest change of all, it's no longer plain text. You can no longer tell that to a system, write a couple of commands, and expect a response back. It is based on Google's Speedy protocol, which has been around for a while. Speedy has been discontinued in favor of HTTP 2. So the spec, the basics on which we are now working, is in part formed by Google. Of course, not only them, a lot of people in the community are involved. It uses a concept of multiplexing. Well, you're talking HTTP 1. Whenever you send a request to a server, you open a TCP connection, headers, and you get your data back. Potentially, you close the connection. With HTTP 2, you're only going to open one connection to a server, no matter if you want one response or 5,000 responses. It's on that one TCP connection, and because it's now binary, you can mix and match multiple requests in the same connection, that you can have one connection and have request and response with multiple resources. If you do that in an HTTP protocol, or the plain text protocol, you wouldn't know the response you're getting back to if it was the first, the fifth, or the second request that you made. When it's binary, you can make the protocol like you want it, that doesn't really matter, and you have more control over requests that are going back and forth. It supports something called server-side push, we'll get back to that later, and a concept of request priorities. First of all, who understands HTTP 2? There are two major players, of course. You have the clients, user agents on one hand, and the servers on the other. If you are lucky enough to have a technical audience, 9 times out of 10 you'll have either Firefox or Chrome browsers. They support it no matter what. If you are unlucky and you have some non-technical users, you may see some Internet Explorer. It has partial support since IE 11, which is only available on Windows 10. So anyone lower than Windows 10 on IE cannot understand HTTP 2. Doesn't have to be a problem, it just means the browser doesn't understand it. Mobile browsers are especially lacking, which is a shame because on mobile it could make the biggest difference out of all. Server side, of course we need something to generate the data. If you are running Apache, there's a mod HTTP 2 module available for you. That is if you're running Apache 2.4, which most servers don't. Most understand Apache 2.2. Nginx also supports it. They call it a beta. It works flawlessly. We've been running it for, I think, about a year now since it's been released. But officially, it's a beta. It requires you to enable their new line or mainline repositories. But it works like a charm. Microsoft, even though their user agents, their IEs, do not really support it, has support for it in IIS 10, which is not yet publicly available, so we'll call that a beta as well. And there are, because the major player did not implement HTTP 2 fast enough, a lot of new players came to the scene and thought, this is our opportunity to seize some of that server power and run our own. We have H2O, NG, HTTP 2, and Caddy are the most popular HTTP 2 proxies / web servers you'll see today. So if neither of these can run for you, you could perhaps run one of these in front of your normal web server to have it serve HTTP 2. Bottom line, the client side is 9 times out of 10 it's covered. The client will support it, meaning your Firefox or Chrome's. Server side, it could be a bit tricky depending on the server stack you are running, the versions you are tied into. The benefits. What is the actual benefit? Why would you enable HTTP 2 instead of just leaving this room right now and never looking at it again? Is it faster? Does it use less resources, or is it even heavier? Could it offer better bandwidth usage? Does it offer more control on the server? Because right now it's the client, the user agent, that pretty much controls everything that happens. So we'll dive into each one of those. First of all, nowadays we have a concept of domain sharding. If you haven't heard of it, here's a small recap. Anytime a browser tries to load a web page and it contains 50 images, if they're all loaded from the same domain, a browser will open 6 to 8 connections for each of those assets. That means if you have 50 images to load, it'll do them in blocks of 8. First the first 8, once one of those requests is done, it'll start the next one. That looks like this. If you want to load a web page, This one, for instance, has just 200 images, so perhaps not a really realistic example, but it shows what's happening. The first 6 are downloaded straight away, and as soon as one of these is finished, it'll start the next blocks of 6. It does so because it is trying to protect both the client and the server and not overload the server. Because for each of these images that it's trying to load, it has to open a TCP connection. And TCP connections are something we don't really have to think about, they just work, but they are pretty expensive on the network end. I'll cover that a bit later as well. So this is what domain sharding, or this is what the default browser does. It loads them 6 at a time. Domain sharding is when we try to get smart. Instead of just going to your site.be/image1 until 50, we go to subdomain 1, subdomain 2, subdomain 3. The idea is to trick your browser into thinking it's not connecting to the same web server, but a different one. So we can open multiple connections at the same time. And this works. This works really well, actually. You're tricking the browser, so you have to be careful when or when not to do so, but this works. But there are some downsides, of course. You first have to do a DNS lookup, which also may not sound very heavy, but adds a couple of milliseconds to your request. You have to open a new TCP connection, which if you're familiar with the low-level specs of networking, requires a 3-way handshake, meaning there are multiple packets going back and forth to negotiate your connection before you can even request the next piece of data. And it introduces another TCP slow start. Slow start is a congestion algorithm to prevent, let me describe it another way. If I am a client and I'm connecting to Wim, the server, I don't know what speeds Wim understands. So we start our connection off very, very slowly. And gradually I'll crank up my connection with just sending a bit more data, and just a bit more, and just a bit more, until Wim no longer sends me a response anymore. At that point I know the previous value, that was my maximum. But that takes a couple of times, and you can see this if you're downloading a big binary file from a web server. You can see that it starts off slow and gradually ramps up to its final, faster speed. That is TCP slow start. It's slow starting every connection until it knows the maximum. Now, if you're sharding, that means every one of those connections is going to go back and forth between that TCP slow start. So once you know your ultimate speed, so to speak, then it's fast, but it starts off really, really slow, which is especially painful on mobile devices. Well, perhaps not mobile devices, but mobile networks. So despite the downsides that I've just mentioned, domain sharding in HTTP1 is usually still faster than not sharding. But how does HTTP2 try to fix this? First of all, it no longer opens multiple connections. It sees a website, it sees a lot of content, it will open one connection to that website, or web server, and send all those requests back and forth. That has a couple of easy benefits. Only one DNS lookup, no more DNS subdomains, only one TCP connection, and only one TCP slow start. So one 3-way handshake and one very slow back and forth until we can discover the ultimate speed. Multiplexing, as the binary protocol understands it, also has a couple of extra benefits. We can introduce request priorities. I'll get back to that later. And it could mean, or mileage may vary, that we don't have to concatenate all CSS or all JavaScript into one large binary blob. Because, why do we do this today? Because we understand that multiple HTTP connections can be heavy. We try to send our client, the user agent, as much data as possible, even if it means that at that particular page, that 500 kilobyte CSS file only needs 20 kilobytes. In HTTP2, because connections are getting less expensive, we could just generate a CSS file only for that page, meaning less data to go back and forth, less data to parse the CSS file, instead of sending hundreds of kilobytes of extra CSS content that may or may not be needed on that page. The downside, of course, if you do that the first time, it's cached client-side and you no longer have to do the second request. So this is going to be tested on your environment to see if it produces your results. Another benefit or downside, if you're the NSA, HTTP2 is going to push us into TLS and SSL certificates. Now, just to make it clear, the protocol of HTTP2 does not require SSL or TLS. However, major browser vendors, Mozilla, Firefox, even IE, have just decided that this milestone in our HTTP world, is the perfect time to say, okay, the protocol may not support it, but we as browsers will only understand or only speak TLS for HTTP2. If you want to do this on a plain text connection, it won't work. This practically, for you, means that if your site does not have an SSL certificate, you cannot run HTTP2. There is something called H2C, the plain text version of HTTP2, which in the spec, in the protocol, it's allowed. You'll never see it in practice. This can be useful if you want to implement something on your own servers, on your own controlled environment, to get the benefits without the SSL overhead. So we'll have more fun managing SSL certificates, more fun screwing it up and knocking our sites offline. There are, of course, some better tools nowadays. Last year, Let's Encrypt went live, offering free TLS certificates. That definitely helps, but it's still very easy to make a mistake that may not really seem obvious to you, but that could give the user, the browser coming to your site, a very bad experience. Mixed content, not showing images, forgetting an intermediate certificate, making it work on your PC, but older browsers just throwing an SSL error. There's a lot of things that can go wrong here. Another benefit of HTTP2 over the older protocol is header compression. You saw this earlier when you type your headers to describe a request to the server. You don't have to think about should I compress this or not, because headers in the old world are never compressed. Every header that you send or that you receive is plain text. Which could be a problem, because something as, say, cookies are all sent and received in HTTP headers. So if your site or your application sends cookie after cookie after cookie, every request that the user agent makes to the server contains all of those cookies again, which is all plain text, but is not compressed. So this can add up to quite a bit of a size. If we could compress headers, because it's just text, you could easily have 75% of the compression ratio. What does this mean? The protocol or the system behind header compression is called HPAC. Just something to know, I guess. Not really that big of a deal. What does this mean? Just the numbers, but I'll skip to the conclusion. If you can compress your headers both from and to the server, you can reduce the size of those headers by a factor 8 or more if you send more than 4 cookies. Another advantage of the new protocol is called server-side push. What happens in the old world? In the old world, you, the client, the browser, your PHP implementation, you basically decide the priority by sending one request, waiting a bit, sending another request, and sending another request. You put them in an order, and because connections are blocking in that way, you have to wait before the previous command is done. We've seen talks today about parallel and concurrency. The basic gist of it is that you decide as a client what the priority is. For HTTP2, however, you can do something that is magic. It's your user agent is requesting a particular page. You deliver that page, but you immediately send data that the user did not request yet. It's magic. Magic in a good way and in a bad way. Because, let's say, you build Facebook.com. You know that if someone goes to Facebook.com, eventually they're going to want to load the CSS file over JavaScript. Now what usually happens is your browser downloads Facebook.com, the main page, starts to parse the HTML, finds references to files. After that parsing, it'll send off a new request for the CSS files. But you're a developer, you know that if you're loading the homepage, the next thing you'll want to load is probably CSS, or JavaScript, or tracker cookies, whatever. You know this. Wouldn't it be convenient if you could immediately tell the client requesting that response to just ship it as well? You can. It's called a push promise. You're going to push something from the server to the client, which the client can deny, because if you're trying to send it 5 megabytes of CSS file that it already has in cache, it can deny that request. If it doesn't have it, it'll save a bit of milliseconds just to not have to parse the HTML, the entire DOM, and find the CSS reference. Important to know is that it doesn't replace something as WebSockets. There is no client-side, no JavaScript API to manipulate server-side push. It's initiated by the web server. You have no way of controlling it in either code, JavaScript, or just in HTML. Here's what this looks like. Normally, if you request a page, you'll want CSS, but there's a bit of a delay. The delay is between, well, downloading the file on the one hand, browsing the HTML, finding references to JavaScript, the browser trying to be smart and thinking, what should I request first? JavaScript, CSS, perhaps this file. That takes a bit of time and a bit of CPU cycles. If you do this in HTTP2, and I had to use a different server because mine didn't support this, the moment you send your first request, you can immediately send CSS, JavaScript images that you know the client is going to request eventually. This saves a couple of important milliseconds that look as if the browser is just blocking, which in fact it is. It's trying to decipher what the next request is. Server-side push shaves off those couple of extra milliseconds. Now, you're a developer. You're here because you write PHP most likely. How do you manipulate this from within your code? There's a difficult answer. I don't really know, because the web servers trying to implement this feature don't really know. The protocol of HTTP2 clearly describes how a push works, how a web server can push content to a client. What each web server can do, and by web server I mean Nginx or Apache or IIS, they can implement their own way of you telling the web server what needs to happen. What will most likely happen is that you as a PHP developer will set additional headers in your response. Those headers are sent to the web server. The web server parses those and will then translate them to the HTTP protocol to send that additional data to your end client. So you'll set headers to describe your push. The web server hopefully interprets them correctly and sends that push request. For example, there's now one web server that supports it. It's called NGHTTP2, which uses the link header. So if you're a PHP developer and you set the link header from anywhere in your request, NGHTTP2 will receive that request, because first it receives it from PHP before sending it to the web server, or the user agent, parses this, and then it will send along an additional CSS file. Now the tricky part is that this works for NGHTTP2. Nginx may do something else, Apache may do something else, Microsoft will probably do something else. But as a PHP developer, or as a framework developer, let's say you're maintaining Laravel, which header do you pick? You send them all because one of them could be using it? You send none? You make it optional? The problem with the choice that those guys made is that the link header is already used for other purposes. For instance, Chrome, I think last week, added support for preloading URLs. You can already set this header in your code, and if your visitor happens to be Chrome, the link that you're sending in back will already be used in Chrome to do the DNS lookup and start a TCP connection. So that if you want to browse that URL, it's optional. There's already a DNS lookup happening in the background, and there's already a TCP connection. It'll make things feel faster. I think it even tries to pre-render the page in memory. So this header, nice idea in theory, may not work very well in practice. So how does this work? I said it before, you're a PHP developer, you send a header. So if I want to browse your website via Chrome, I'll send my request to the web server, which will in turn execute PHP code. In your PHP code, you can describe additional headers. The web server, let's say Nginx, takes those headers, and then, because these guys talk HTTP2, can send additional data to the client. Once you set your header in PHP, you will no longer have control over what happens at the protocol level. You're handing it off to the web server, to Nginx, and you're hoping that he does a good job at it. But we don't know yet how this will look. Even today, the only ones that actually actively supported are those NGHTTP2 guys, which I'm going to presume you've never heard of. Yes?
I don't, but I really hope that the header route doesn't take hold, because it has one big problem. Links are interpreted when they are finished.
Yes.
So let's assume that your page needs to talk to a database and it takes 10 seconds to have a response back. You could, if there's a hook, a function call to go into the web server, there's no reason why the server-side push couldn't be initiated before that call to the database is made.
Right. To repeat the question, right now, by default, if you're generating a response on the web on PHP, you have to generate the entire response before it's handed off to your web server and before that can interpret the headers. While that is indeed the default behavior, you can also use something as, what's it called? Buffer, not buffering. You can do kind of streams where you can already send, well, in the case of PHP, if you have your output buffer, you can flush it straight away to get the first bits of the page already out, which includes headers. So you could use that to already send additional headers and hopefully have the web server interpret it. But that does mess with compression. Content length is
there's
problematic.
Quite a few reasons why this seems like a very suboptimal choice to me. Eventually,
if whichever web server you're running indeed supports an API that you can then already send additional info to, that would be great. Right now I have no idea if any of them are going to do that. So right now they're all using headers. Well, all. One of them makes it work and one of them is using headers. Does that answer your question?
sure.
Another benefit, we have had server-side push where you can also already send additional data from within your code. There's also something that is initiated from the client side, from the user agents, which is called request priority. It's pretty obscure because there are some gotchas to be had. First of all, your browser, when it makes 20 requests to the remote server, can assign each of those requests a priority. You can say that it prefers CSS over images, or that it wants JavaScript before its CSS file. That's a preference on each request that it can set. The server, once it receives it, can either honor it or ignore it altogether. So when your browser fires them off, it assigns them a priority, and hopefully the server understands that and honors it. You, as a PHP or a JavaScript developer, have no way of controlling this. This happens within the browser, pretty low level. This is just something to know that it exists, or so there is nothing you can do about it. A new benefit of the new protocol, it doesn't really change all that much for us as implementers. We have the same status codes, we have the same response codes. Perhaps not a real advantage, but it's convenient. If you've memorized all of those status codes, good, you can still use them. So PSR7, which we saw earlier, still applies for HTTP 2. Just to recap the benefits. We don't have to do domain sharding anymore. In fact, if we do, we're just making HTTP 2 look like HTTP 1. We'll have TLS everywhere. We have header compression in something called HPAC, which makes every request smaller just automatically. We can use something called server-side push to send additional requests or responses that the client has not even initiated yet. And the browser still has a bit of control, can send priorities or referred priorities. Disadvantages, because not everything is all rose. First of all, it is for the web servers still in beta for pretty much every web server that I know. So yes, the protocol is finished, the RFC is done. It will probably undergo some iterations for improvements. But the protocol is done, not every web server has implemented it yet. So if you want to run this, you will effectively be running beta software. The protocol itself took baby steps. And I put this in quotes because there are a lot of people that are not very happy with HTTP2. However, the move from plain text to binary, the fact that everything is multiplexed, those aren't baby steps, those are pretty big advances. However, this was a pretty big move, HTTP 1 to 2. Perhaps they could have done more. If you want to support HTTP 1 and HTTP 2, it's probably not going to be very simple, because what's good for HTTP 1 may be bad for 2, or vice versa. I'll get back to this a bit later as well. It's not always the case. And it's a new protocol. While there are, like I mentioned, not many web servers that support it, pretty much any client, every browser supports it. However, because a client supports it doesn't mean that the protocol works in reality. There are a couple of potential problems that we may see here. For instance, if you're running some kind of intrusion detection system and you're really strict about what kind of content you allow in or outside of your network, you may be trying to parse HTTP1 traffic. If your IDS is trying to decrypt traffic and it sees traffic that doesn't comply with the old protocol, it could just block your connection. So there are a couple of gotchas to be had when implementing HTTP2. To be honest, in reality, I haven't had a single disadvantage of the new protocol. I've enabled it wherever possible, and nothing went wrong. Let's compare a bit of performance, just to get you warmed up and enable it tonight. If you Google for Gopher tiles, it's a Go project to demonstrate concurrency. What it does is, it's a page, tries to load 200 individual small images, and it's a great example of showing the domain sharding that happens by default. On a normal connection, that takes about 30 seconds to load, because each 6 of those images are blocking after the other one. If you do the same page on HTTP2, so we now have 30 seconds, it's there in less than 1.5 seconds. That is, in terms of responsiveness, in terms of browser client happiness, a world of a difference. The only bottleneck that you have right now is the bandwidth between you and the web server. You no longer have to wait until multiple connections get built because multiple requests are blocking on other ones. This is an advantage you get right out of the box. Now, a couple of conclusions to wrap it all up. If your application today is slow, it's probably going to be slow on HTTP2. This won't fix that. However, if you already have a very fast application, simply enabling HTTP2 will probably make it faster as well. If you want to support HTTP2, it's probably pretty simple if your web server supports it. It's probably one flag you have to set in your web server saying, yes, I want to use HTTP2. For the client side, you probably don't have to matter unless your market is very old Android devices that are never going to get updated. If you want to optimize for the old and the new protocol, it's probably going to be a bit of a challenge, because for the old protocol, domain sharding was the way to go. For the new protocol, you probably want to do that as little as possible to make use of the multiplexing, the single TCP connection, etc. But perhaps the most important one, if you already have an application that is running on HTTPS, just enable HTTP2. While your application is probably not optimized for it, there are already advantages that you get out of the box. Header compression, multiple connections over a single TCP connection, that's just going to make everything feel faster. The next step is determining, out of my user agents that I see in my logs, is it worth it to optimize for HTTP2 or not? And that was the end of my presentation. Sort of on time. If you have any questions, yes please.
How about firewalls, like level 7 or protocol level?
Those are going to be tricky. Perhaps the advantage of, well, the HTTP2 exists in two flavors. We have the unencrypted version that you'll probably never see, and you have the encrypted version. If your firewall doesn't decrypt traffic, most firewalls don't, it'll just see that as an encrypted set of data and nothing will happen. It'll just pass it through. It happens on the same ports, no difference. If you have one of those firewalls that decrypts traffic, they could get confused because they might expect an HTTP1 session trying to decrypt that, while parsing an HTTP2 connection is suddenly binary and that may be blocked. So that is tricky. Yes?
Do push files have their own headers?
The push files have their own headers, yes. Wait, I said that too quickly. I'm not sure anymore. Thinking about it. It's a good question.
Because caching would be very hard without that.
The client, the user agent, can deny that. You know the answer?
Actually, there should be no difference with a push response, so it should be possible to
I think every request that you should normally get is also included in the response in the early push. So the client knows when to deny a request.
question about the files. I guess it depends on the files for those who do decrypt the SSL, because HTTP2 uses an upgrade mechanism, so the initial phase of the connection is actually HTTP 1.1, very specific suite which is HTTP 1.1. So if the firewall disrupts this upgrade mechanism in some way, the connection will automatically stay in HTTP 1.1. Sorry?
There's a fallback.
There is a fallback.
The downside is, you'll have to test your firewall to know how it reacts. And if you have agent firewalls which are not updated, that could be a problem. Yes?
You said that the server-side push is going to save you about 50 milliseconds for the browser to wait for the page to load and identify the resources. Is it going to be word optimized for it? Because it will probably only happen in the first request. Because in the second request, the CSS and JavaScript might be already cached.
That's true. However, the server answering to your request does not know if you already have that file in cache. So we'll try to send it every time if push promises or server-side push is enabled. However, if your client starts to receive a CSS file, it can already determine that it has it and block the connection. But the push should happen every time. So the overhead, I think, is still minimal. But you are right, the advantage is really only in the first loading of a page.
There is work being done right now on this topic inside. There's a concept which is being discussed, which is called hash digests, which a server can put into the client, digest with a certain algorithm of some resources the client should have, and so the client can make decisions based on that.
That's even better. Yes?
I was wondering, since you mentioned multi-placing, does it have any provisions for AJAX calls as well? I mean, do they still go through the same TCP connection, or do you open a new connection since the page is loaded?
Depends on the server. If your server supports Keep Alive as a feature, it should. If it's still within the Keep Alive timeout, reuse that connection. However, if you don't support Keep Alive, say you've done all your requests and you end your TCP connection, well, then it has to start a new one. Yes?
Is this going to end the DDoS attacks?
Not at all. No. It's just another protocol to send traffic over. They're using the old protocol, they will use the new one as well. However, because of the encryption, there is also overhead client side to initiate the TLS encryption connection. However, that overhead is minimal in terms of DDoS.
Yeah, but right now you can exploit that every time you send request to open a connection. So this at least will be like beneficial.
You mean if it's initiated client side by sending AJAX requests to your target?
Yeah.
You can still take that if you use subdomains. Because for the browser, each subdomain is a new connection that will start a new connection. Yes?
Very basic question. So the first connection on the client, it's connection port 8, I suppose.
Yes.
And
Well,
it sends you get in plaintext, and then this protocol is
yes. What happens is first, if you connect to port 80, you don't know if your remote end supports HTTPS. I think Firefox or Chrome now sends an upgrade in secure request header to indicate that it would prefer that connection over HTTPS. The next step is that the web server would answer with a 301 or 302 response saying, okay, you can also get this on HTTPS. And that's when the browser could, its first connection will always be HTTP1, and then it can negotiate the rest of the set of connections over HTTP2. However, if you use something like HSTS, the strict transport security, you can alleviate some of those problems by having only the very first request enter on 80. And from then on, the browser will cache it as 443 and just remove or continue on HTTPS.
When answering an earlier question, you said that you don't see much of a future for HTTP2 without encryption, so without TLS. Does that mean that you predict that most servers will start to use TLS, or do you predict that most insecure websites will continue to use HTTP 1.1?
Mostly the latter. Browsers, I don't see them ever implementing HTTP2 over plaintext, so they've made that decision, which is a great decision, I think. However, if you also happen to be implementing your own protocol, your own web server and client for a very niche market, you can do whatever you want. If you run HTTP websites now, I don't see you enabling HTTP2 anytime soon. Any more questions? Yes?
Since the new protocol is in binary, how can you debug it if something doesn't work correctly? You can't just run TCP dump anymore.
TCP dump is one of the only ones that won't work as you expected. However, there are network capturers that can decode HTTP2 traffic. So the moment you've already deciphered it, because it's TLS, which is problem number one, once you overcome that hurdle, there are ways of displaying HTTP2 as if it were HTTP1. In fact, if you look at your browser, which is very hard if you don't have internet connection. This won't work, I think. I was trying to show this. So your current tools to use HTTP2, curl, your browser, your network inspector, they all do that transforming of binary to text for you. So if you open your inspector and you're used to seeing headers, they look a bit different. They're prefixed with a semicolon, but they are still headers that you can see. So for us, normal folks, we probably won't notice the difference. If you're used to running curl or HTTP, that still works. The output is still the same. However, if you want to implement a web server, that's when it gets a bit more tricky. Yes?
If the content length header is binary, does it have an upper bound?
I have no idea.
I know there's a limit to the number of screens that can be opened on a TCP socket, which is 2 to the 31.
Probably won't read that.
You actually, I don't think you will need a content type anymore, because the framing takes care of it. So HTTP2, the multiplexing works by splitting the responses and the questions in chunks, which are intermingled with each other. And there's a special frame type which says end of string. So I'm not sure really, but I don't think content length will be as necessary as it is now with HTTP1, because the protocol takes care of saying and done, but still keeps the TCP session alive, which is the end goal.
Yes, makes sense. From now on, we'll just ask these all the questions. I'll repeat them for the video. Anything else?
Just one question.
Yes.
If the server replies with a HTTP1 header inside a HTTP2 connection, will block the client?
No. The moment you are in an HTTP2 connection, you're already talking binary, and you can actually send any kind of header you want. The protocol is already negotiated at that point. I'm not sure what would happen if you do the reverse in HTTP1, respond with a unknown version. I think some clients might trip over it. Others may just ignore it altogether. Anything else? Okay, thank you very much.